Hello. Hi, Joanna.
Hi, ma'am.
How are you?
Hi, ma'am.
Sorry for being late. My ID was log out on its own. Okay. Till which topic did we did yesterday?
Ma'am, we finished oxidation states.
Okay. Then two more theory parts are left. One is the trains in the standard electrode potential for M2 plus 2M, and then it is M3 plus 2, M2 plus. And the last is the trend in stability of the higher oxidation state. Then we have chemical reactivity, magnetic properties. Okay. So let's start. Have you revised the previous part?
No, ma'am.
Okay. What have I explained you yesterday about enthalpy of atomization?
Yes, ma'am. You explained about it.
I know I explained about it, but I'm asking what was it?
Okay. The heat required to break the metal lattice to get free atoms. That is enthalpy of atomization.
And why do transition metals exhibit high enthalpies of atomization?
Because they have metallic bonds. No, they have covalent bonds.
So what is the result of they
Because
having the strong bonds?
strong, so they will require more energy to break it. So thus they'll have high enthalpy.
And why do they have strong? How can they form the strong bonds between atoms?
Uh, they have unpaired electrons.
Yes, they have large number of unpaired electrons. That is why which elements have low enthalpy of atomization?
Zinc, cadmium, mercury.
Yes, because they don't have any unshared pair of electron. Okay.
Yes.
Okay. Now the next topic is we will be seeing the trains in M2 positive M standard electrode potential. Okay. Now, there is no regular trend for the E naught value. Do you know what is standard electrode potential and electrode potential?
No, ma'am.
Difference between electrode potential and standard electrode potential. Know it?
No, ma'am.
Okay. What is electrode potential? The symbol for electrode potential is E, or we can say to be EMF, or we can say to be E of any cell that we are finding, that is in electrochemistry. But the representation of this electrode potential is E. And the representation of this standard electrode potential, it is E naught. Okay. So here we will be seeing the trends in M2 positive to M in the standard electrode potential, and it is E naught. So what I am saying that there is no regular trend in the E naught values of M2 positive to M values.
And what is
Why
this
there?
M to M?
M2 plus is M is any metal which is in 2 plus oxidation state, and it will get reduced into this. Okay. So because of this reduction from M2 plus to M, it acquires a reduction potential. Okay. Or we can say that it has a standard electrode potential. In detail, this I will be teaching you in electrochemistry. Okay. Where we will be talking about the cells.
Yes,
Now, there is no regular trend in these values. Why it is so? Because their ionization enthalpies, okay, they do not show a regular trend. Okay, that is why the reduction potential, it has no regular trend. Before to this, I want to tell you that one important thing, that smaller the reduction potential, smaller the reduction potential. Now reduction potential we will be seeing for M2 positive to M. It is showing reduction here. It is going from 2 plus to 0. Okay, so the electrode potential we can call it as reduction potential. For example, if it was showing us oxidation, then we would have called it as oxidation potential. So smaller the reduction potential for the system, which system we are talking? Any system, Mn positive to M, more stable is the oxidation state of transition metal in aqueous solution. Okay, so smaller is the value for the reduction potential, more stable is the oxidation state. Okay, now if we have here higher the reduction potential value, less stable is the oxidation state of the transition metal. Okay,
yes,
now this was a journal point which was before this point. Okay, now I will be writing this point again. This was a general trend. Now we will be talking about the trends that we follow. What had I written? That no regular trend in the E naught M2 positive M values. Okay, no regular trend is there. If I see the graph, if I plot for standard electrode potential and the elements, for example, here I have the standard electrode potential E naught, that will be in volt. Okay, so here I have -2, -1.5, -1, -0.5 and 0. Okay, this is the baseline. Now we will be talking about the reduction potential. So those reduction potentials will be with negative sign. If we talk about oxidation potential, then those reduction potentials will be with positive sign. Okay, now I am taking here elements: titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. Okay. Now for titanium, the value is -1.5. Okay. Then it increases till chromium. Then it decreases for manganese. Then it is going up till -0.5 for iron. For iron, it is increasing. For manganese, it is decreasing. And for chromium, again, we are seeing that peak. Okay. Then one value I'm showing here like this. It is crossing that barrier for copper. And then again for zinc, it is decreasing. So this is the general trend that we are seeing here. Now, why is this general trend? If you see the E naught values for manganese and zinc, for manganese and for zinc, they are more negative than the expected from the general trend. Now, what is the general trend? This is the normal observed values. These are the observed values which I have shown with pink. Now, if I see the general trend, then the general trend will be slightly like this. Here, then it is on the same line, then it is like this. Okay, Now, if I see for manganese and for zinc, then the value is more negative than the expected value. Why it is so? Because if you see the configuration for manganese, what will be the outer electronic configuration? Yes, Joanna, what is the configuration for manganese?
What is the atomic number of it?
It is 25.
Then 4D5 will be 3D, sorry, 3D5,
And
4S,
4s,
1, this one.
this is for chromium.
And
Manganese
4S.
is D5, 4s2. Okay. It has both, this is half filled and this is fully filled. So manganese is a stable configuration, okay, in the ground state. If I see for zinc, what is the configuration in the ground state?
3D10, 4S2.
3d10, 4s2. Now, if you see the configuration, then this is the half filled d orbital, the s orbital is completely filled, and here d orbital is completely filled and s orbital is half filled. Okay, so because of the greater stability of half filled orbital in manganese and completely filled in zinc. Okay, now the ground state for manganese was 3d5 4s2. Okay, and for zinc it was 3d10 4s2. Now we were writing the reduction potentials for M and M2 positive and M. Okay, then the excited state will be when it will be losing 2 electrons. Okay, if it is losing electrons, then also it is in the stable configuration. If zinc is losing 2 electrons, then zinc is also in the stable configuration. So because of this greater stability of half filled orbital in, we can say for Mn2 plus and completely filled in Zn2 plus. Okay, they have more negative value. They have more negative value than the experimental one. And what we have studied earlier, we have studied that smaller the reduction potential value, more stable is the oxidation state. Okay, so if the stable oxidation state is this Mn2 positive and Zn2 positive, because they are getting the stable configurations, so these are the stable oxidation state. So if stable oxidation states we are getting, then the value of reduction potential will be smaller. Okay, because of that reason they are getting more negative value than the experimental value. Okay,
Salt is also having negative rate.
Expected value, more negative value than the expected value.
Cobalt is
Yes.
also have, right? Why?
Wait, more negative value than the expected value. Yes, what are you saying?
Ma'am, I'm saying cobalt is also having more negative value, right?
This one was the observed value. The expected value is the green. Okay, cobalt is having more value than the expected value. Okay, more value than the observed value. The green graph, the green one is for expected. For manganese, it was lower, and for zinc, it will be lower. Here it will be. Okay, so these two were those elements which have more negative value, more negative expected value than the observed value.
Okay.
Okay. Yes. Now we did for manganese and for zinc, and did okay. Now there is a question that why is chromium 2 positive reducing and Mn3 plus oxidizing when both have D4 configuration? Let's do this question. What it says that why chromium 3 positive it is reducing, okay, and why Mn3 positive it is oxidizing. Okay, if I see the configuration for this Cr3 plus, it is, what will be the configuration? What is the ground state configuration for chromium? And then tell me the excited state one. And same is for this. Ground state configuration for chromium.
3D 5 4s1.
3D5 4s1. And excited state when it is in Cr3 positive, what will be?
3D 3D3.
3D3.
Then for
It
manganese,
is, sorry, it is Cr2 positive. Okay, this will be Cd4. For manganese, it is Mn3 positive. Manganese is ground state
3D5
3D5.
4s, and then excited still 3D4.
Yes. Now the question was why Cr2 plus it is reducing and Mn3 plus it is oxidizing when both have D4 configuration. Okay, this was the question. Now, can you guess the reason why it will be like this?
No, ma'am, I don't know.
Okay. Now, if you see, then we know that chromium, it can show two oxidation states. Okay, it can show from chromium 2 positive, it can reduce to chromium 3 positive. Sorry, it will increase in oxidation state. Chromium shows two oxidation states. So if I see for chromium 2 positive, then it is in D4 configuration. If I will see for chromium 3 positive, it will be in D3 configuration. Okay. Now for manganese, it is shows two oxidation states again. The most popular one here, it is Mn3 positive, and the next oxidation state, the change is from Mn2 positive. Okay, because Cr2 plus it is showing the reducing character, so we will be taking the oxidation state, the higher oxidation state, and here it is oxidizing, so we will be taking the lower in oxidation state. So in Mn3 positive it is in D4 configuration, and in Mn2 positive it will be in D5, right?
Ma'am, I'm not understanding.
The question was why is Cr2 plus reducing and why is Mn3 plus oxidizing? Okay, I told you one thing here, that smaller the reduction potential, more stable is the oxidation state. Now they are saying that Cr2 plus it is reducing. That means we will be comparing with its oxidizing value. Okay, So Cr2 plus, the next value, the next element will be with 3 plus oxidation state. Okay, here we have to prove that Mn3 plus it is oxidizing. So we will be taking the opposite one, the reduced oxidation state. So I am comparing the outer shell d orbitals, comparing the electrons in d orbitals. In Cr2 positive it is d4 and Cr3 positive it is d3. If I compare for Mn3 positive it is d4, for Mn2 positive it is d5. Now if you see that we are going from d4 to d3, and here we are going from d4 to d5. First I'm comparing for manganese. In manganese it is achieving the more stable configuration, right?
Yeah.
Okay. And if it is achieving the more stable, uh, I would say configuration, it is acquiring extra stability. So that means that Mn3 plus will be oxidizing in order to gain that extra stability.
Yeah.
Okay. If you see for chromium, why it will be reducing? Because here we have D4 and D3. Okay. Now, have you done that EG and T2G levels? What are EG,
Have you done
T2G levels? T2G and EG levels.
what is that?
Have you not done in chapter number? Okay, you have not done coordination compounds yet. So you will be doing there. These are the two, for example, you have your d orbitals. Okay. Now these d orbitals, they split into two energy levels. It will be, the lower one is T2G. Three orbitals will be here, dxy, dyz, and dzx. Here these are dxy, dyz. What are the five d orbitals? It is dzx. This one will be dx square minus y square, and this one will be dz square. Okay. This will be splitting. The lower level will acquire these three orbitals, and the higher one will be 2 dx square minus y square and dz square. Now, if you see that we want to fill these D3 electrons, so the lower energy levels, they are always filled first. So I'm filling 3 electrons here. Okay, this is for D3. Now the same thing, if I'm drawing for D4, it will be like this. 1, 2, 3. Okay, now it can be here also and it can be here also. If you see this, so it is the degenerate level. Okay, so it is the half-filled configuration. Okay, and here the electron, it can go to this orbital also, it can remain here also. Okay, so that is why Cr2 plus will be oxidizing, because when it is oxidizing, it is going from D4 to D3. Okay, this degenerate orbitals, they are comparatively more stable, we can say, in comparison to the D4 configuration. That is why Mn3 plus it is oxidizing and Cr2 plus it is reducing. Okay, this part of T2G and EG, you will understand more when we will be doing the coordination compounds, that how d orbitals they are splitted. Okay.
Yes.
Okay. Now this was the trend that we were seeing for M2 positive to M. Now the second trend we will be doing will be for M3 positive, M2 positive standard electrode potential. Okay. Now, if you have your NCRT book, please open it to table number 8.2.
Yes, ma'am. Done.
Okay. Now I am speaking and you see that table. Okay. If you compare the E negative values for M3 positive. The last second row you will see M3 positive to M2 positive.
1 second, 8.2, right?
Yes, the electronic configuration and some other properties of first series of transition elements.
Yeah, okay, got it.
Got it?
Yes, ma'am.
The last second row. If you will see then the value the value of E node it shows the varying trends. First it is minus 0.37, then it is going to minus 0.26, then it is increasing, decreasing, increasing, decreasing like this. So why it is showing various trends? If you see for scandium, the configuration for scandium is 3D1 and 4s2. Okay. Prior to this, we have a noble gas element. So I am writing here noble gas element, and then it is 3D1 and 4s2. Okay.
Yes, ma'am.
Okay. Now, if scandium is in 3 plus oxidation state, then it is losing 3 electrons. That means it will be acquiring the configuration of a noble gas element.
Yeah.
Okay. So because the noble gas element configuration is very stable, that means that it will be having the lower value of reduction potential.
Yeah.
Okay. First one is done. Now the second one, see the zinc value for zinc. Value for zinc, it is not given. Why it is not given? See. Okay. In zinc, the configuration is 3D10 and 4s2. Okay. So if this M3 positive to M2 positive means that we are going from one oxidation state to second oxidation state. Earlier we did for M2 positive to M, that means we were skipping, we were jumping to two oxidation state below. Okay, now see here zinc, it is 3D10 4s2. Okay, if we want to remove the electron from this stable D10 configuration to form zinc 2 positive, if it is zinc 2 positive, then the configuration will be 3D10.
Yeah.
Okay, now D10 configuration is very stable.
Yeah. So we'll have low
Okay,
electron.
yes. Now comparatively, if we compare for Mn, manganese, okay, when manganese it is 3D5 4s2, and similar is the case with manganese, it is Mn2 positive and 3D5 we have here. Okay, now this will also have a lower reduction potential value, but this reduction potential will be higher to zinc, right? Because this is the fully filled configuration, so it will be obviously more stable than the half filled one. Okay.
Yes, ma'am.
Okay, now the second one we are seeing for iron. For iron, the configuration is 3D6 4s2. Okay, if it is Fe3 plus, then it will be acquiring the half filled configuration. Okay, then if I compare for manganese and 3D5, then comparatively lower value will be for iron. Okay, if you compare for manganese and iron, for M3 positive, the lower value is for iron, right?
Ma'am, why not manganese?
No, I'm saying you to see in the table. It is plus 1.57 for manganese, and for iron it is plus 0.77.
Yeah.
Okay, now if you see that value, then the lower reduction potential value is for iron. That means that iron will be more stable than in comparison to manganese.
Yes, ma'am.
And which oxidation states we are comparing? We are comparing the manganese in 2 plus oxidation state, and for iron we are comparing with 3 plus oxidation state. Okay, so the comparatively lower value, okay, it is related to the stability of the half filled orbitals. Okay, this much we have to do in this part. Okay, we have to compare with the table only. Okay.
Okay.
Okay, so okay, now the next topic is the oxidation state. Oxidation state, right? No, trends in the stability of higher oxidation state. Okay. Before to this, we will be doing the topic for magnetic properties. Okay. More boring session is there, and something interesting we will do now. Okay. Magnetic properties. Okay. Now, in solid state, you must have read, or in any chapter, you must have read that the atoms with unpaired electrons, they are known as paramagnetic.
Yes, ma'am.
Paramagnetic. And those with paired electron, it is diamagnetic. From this topic, you will be getting formula based question only. Okay. Diamagnetic paired electron, these are known as diamagnetic atoms. Okay. Now,
Yes.
greater the number of unpaired electron, greater is the magnetic moment and paramagnetic character. Okay. Now, in this, we need to calculate the effective magnetic moment. And the formula we need to learn is effective magnetic moment. It is mu effective. Okay. It is under root of n into n plus 2 Bohr magneton. Now, what is this n? N is number of unpaired electron. And Bm is Bohr magneton. This is the unit for effective magnetic moment as it was in dipole moment. Remember, in dipole moment also we have this same unit for Bohr magneton. Okay.
Yes, ma'am.
Okay. Now we will be taking different elements in their ionic forms, and then we will be finding the value of unpaired electrons, and then we will be proceeding. For example, I will be taking scandium 3 positive, Ti4 positive, copper positive, zinc 2 positive, wait,